But for our model in this today's lecture, we're going to use a deterministic model, which is much simpler to understand. So once we decide about the model structure and the model methods, we need to set up their model. And this is very important parts in mathematical modeling of infectious disease. Set up the model, because you use difference equations here or to try to predict the changes. So we will use what we call difference equations. The difference equation is generally expressed in terms of time steps on daily, weekly, or yearly. So with difference equations, we can be able to express the number of individuals at given time plus one, for example, tomorrow, in terms of the number of an earlier time. Simply, it means that I can predict what will happen tomorrow based on what I know today. So tomorrow can be predicted by the information that we have today. And then when you arrive tomorrow, you can predict the information that you have on that day to predict the following day. So we're using the time t, the information at time t, to predict the information of time plus one by using difference equations. It's very simple to understand. For example, we have the susceptible here. Let's try to predict how the number of susceptible changes over time. So we have our susceptible group, infectious group, removed group. So when we want to predict how the number of susceptible changes, we just want to know how many people get out of this box every day. Time plus one, time plus two, how many people go outside and how many people remain here. And in that way we can predict. The risk of infection, the risk of someone who is here to become infectious is generally noted lambda t. It is the transmission probability times the number of people who are infectious. Simply, in this classroom here, if no one has influenza, the risk of infection here is 0, because no one in this classroom has influenza. So the risk of infection depends on how many people have the infection in a population. No people means the risk is 0. But it doesn't only depend on how many people have the infection, but it also depends on the transmission rate. What is the probability that the transmission will happen even if some people have infections here? So let's see it now. Here we have 2 people who became infectious. They have to leave the box. So the 2 here, it's the number of those who become infectious at time plus 1. So 2 has gone. And the formula to calculate how many people becomes is this one here, lambda t. Lambda t, remember, is the risk of infection multiplied by the proportion of susceptible. So if we want to predict the changes here, the number of susceptible at time plus 1, it's the number of susceptible that we have today minus the number of those who went out. It's this one here. So by just subtracting this group here, we predict the number of those who stay here. And it can go on and on the same scenario, we can do it on and on. For example, 2 more people become infected. So these one are the newly arrival, and we can predict for many other cases. So this equation here is very important because it is estimating the number of people that remain here by each time step, like time plus 1, at time plus 2, you can continue time plus 3. So now we are here, infectious. We can also use equation to predict the number of people here who are staying here every day. In a very intuitive way, you know that some people will come here, so there is a plus, and some people will leave this box, so there is a minus. So we have a plus and a minus. So we have the new people here. It's the number of newly infected people. And we have a minus. This is the one who become immune, leaving the box. It's given by this formula here. The recovery rates multiplied by the infectious here. So to predict the number of infectious, we just need to know the number of people who are there at time t plus the newly arrival, those who were here, who came in this box, minus those who recovered here. So these equations here help us to predict the number of infectious people here. The next, we want to predict the number of people who are removed, so who become immune here. This is also much easier. It is based on the risk of, the recovery rate, R. So how many people leave the infectious box to join their removed box? This one becomes infected, comes there. So the risk of recovery is just noted by R, multiplied by the number of infectious, tells you the number of people who become removed. And we have our equations of the number of people who becomes removed at time plus 1. So with the 3 equations here, we can predict the movement of individuals from one box to another box, and over time, at time plus 1, time plus 2, time plus 3. So we can just use these equations here. The 5th steps after making the equations, you need to specify the model inputs. They call it model quantification. Model quantification means you need to tell the values for each of the parameters in your model. For example, lambda t is the risk of a susceptible to become infected. You remember, they also call it the force of infection. We need to know the value of lambda t. R, which is the recovery rates, the risk of infectious to recovers becomes immune between t and t plus 1. We also need to know the value, so we need to quantify our parameters. So this process of quantifying the parameters is called model quantification. And most of the time you will find the information in the literature review, during the literature review stage, when in the beginning. So you want to know what is the R naught and what is the risk of transmission as well as the risk of recovery. For example, remember the force of infection is the transmission probability times the number of those who are infectious in that population. So this is the formula. As I mentioned, if no one is infectious, the risk of transmission or the force of transmission is 0. So the number of infectious people in a population or a given population gives you an idea about the risk of transmission in that population. Regarding the recovery rate, how long it takes someone who was infectious to become immune, you can estimate it by just doing 1 over the duration of infectiousness. So if you know the duration of infectiousness, you know the risk of transmission rate. So we have a lot of challenges. We have lack of reliability data. Sometimes it's really hard to find reliable data. Sometimes you need to collect new data when you do the modeling. And sometimes there are some very sophisticated techniques for estimating some mathematical models. Then we have the model validation. As I said, the model validation is the stage where you need to compare the results of your model with the other models that are looking at the same thing. And then you can use your model for prediction to see how many people changes in each of the box, infectious, susceptible, and immune. And there are softwares to do that. What I use is the Berkeley Madonna, but you can use a very simple Microsoft Excel to do a very simple mathematical modeling. For example, for this exercise, just with an Excel, you can have this kind of estimation, and you can estimate the number of susceptible inputs and infectious disease. So this is just a simulation of how the transmission can happen over time, the number of infectious, the number of immune, and the number of susceptible. So this was just to give you a very, very short introduction about mathematical modeling. And for those who are interested and for more questions, you can come in our department for discussion. And sorry for taking too much of your time. Thank you very much.